And we'll talk right now about the connecting rod. The connecting rod is used to transmit the pressure applied on the piston to the crankshaft. Connecting rods are able to swivel at the piston and the crankshaft. This allows them to freely move the piston up and down while they rotate around the crankshaft. Connecting rod faces a great stress. The force applied during the power stroke is applied to the connecting rod as it moves through a variety of angles. The rod has a great force applied to it from the top and has a great resistance to movement at the bottom. So the center section of a rod is basically an I-beam. This provides a maximum strength with a minimum weight. Connecting rods are kept as light as possible. They are generally forged from high-strength steel or made of a cast iron. Cast iron is rarely used in automotive engines, and aluminum and titanium connecting rods are also used. Aluminum rods are light and have the ability to absorb high-pressure shocks, but they are not as durable as steel rods. Titanium rods are very strong and light, but they are expensive. Also, we have the piston pin, which connects the piston to the rod, and the piston pin can press fit in the piston and free fit in the rod. When this is the case, the small end of the rod will be fitted with a bushing. The pin can also be a force fit in the piston and pressed fit in the rod. In this case, no bushings are used, and the pin simply moves in the piston using the piston holes as a bearing surface. The big end of the rod is used to attach to the crankshaft. This end is made in two pieces. The upper half is part of the rod, and the lower half is called the rod cap and is bolted to the rod. The connecting rod and its cap are manufactured as a unit and must always be kept together. Also, we'll move right now to the piston and piston rings. The piston forms the lower portion of the combustion chamber, and the pressure from the combustion are exerted against the top of the piston, called the head or dome. A piston must be strong enough to face this pressure. However, it should also be as light as possible. This is why most pistons are made of aluminum or aluminum alloys. Aluminum pistons alloyed with a copper, magnesium, nickel, and silicon or common silicon is the most common element mixed with aluminum to make a piston. Silicon makes the piston more resistive to corrosion and improves its strength, hardness, and wear resistance. It also helps to reduce the piston's weight. The head of the piston can be flat, concave, convex, ground, raised and relieved for valves, or notched for valves. Newer pistons are typically flat with valve notches, or have a slightly dished crown, and the dished crown concentrates the pressure of combustion at the thickest part of the piston head. Right above the top of the piston pin boss, the piston pin boss is built up area around the bore for the piston pin, sometimes called the rest pin. The pin bore is not always centered in the piston. It can be offset toward the major thrust side of the piston, which is the side that will contact the cylinder wall during the power stroke. Piston heads are often coated with hard anodizing ceramics or electroplating. This coating increases the hardness and resistance to corrosion. And just below the dome, around the sides of the piston, is a series of grooves. The grooves are used to hold the piston rings. The high parts between the grooves are called ring glands. Some pistons have a ceramic coating in the top ring groove to prevent the ring from being welded inside the groove. Normally there are 3 grooves, 2 compression and 1 oil control, and the compression grooves are located towards the top of the piston. The depth of the groove varies with the size of the piston and the type of the rings used. So the oil control groove is the lowest groove on the piston. They are normally wider than the compression ring. Grooves and half holes or slots to allow the oil to drain. The positions of the ring grooves vary with engine design. Many newer engines have the top compression rings as close as possible to the piston head. This reduces the amount of fuel that can drop down the sides of the piston before combustion. This hidden fuel is not involved in the combustion process but leaves the unburned hydrocarbons during the exhaust stroke. The area below the piston pin is called the piston skirt. The area from just below the bottom ring groove to the top of the skirt is the piston thrust surface. There are 2 basic types of piston skirts, the slipper and full skirt. The full skirt is used primarily in truck and commercial engines. The slipper type is used in automobile engines and allows the piston through thrust surface for normal operation. A slipper skirt also allows the piston to be lighter and reduces piston expansion because there is less material to hold heat. There are many terms are used to describe the design of the piston. We will mention some of them. Compression distance or height, the distance from the center of the piston pin bore to the top of the piston. We have as well ring belt, the area between the top of the piston and the pin bore where the piston rings are installed. We have heat dam, a narrow groove cut in some pistons to reduce heat flow to the top ring groove. Also we have the land diameter, the diameter of the ring land on some pistons. The land diameter will be the same for each ring. We have as well the groove root diameter, which is the diameter of a piston measured at the bottom of a ring groove. The root diameter of each groove may vary with the type of ring used. Also we have the top groove spacer, a steel spacer installed above the ring in a reconditioning groove to bring the ring size clearance within specifications. Also we have the piston pin bushing, and we have the major thrust face and minor thrust face skirt, which is the clearance or the difference between the diameter of the piston skirt diameter and the diameter of the cylinder. We have the piston skirt taper, which is the difference between the diameter of the piston at the top and the bottom of the skirt. And we have the piston cam, the shape of the piston skirt area, which provides correct cylinder wall contact and the clearance. We have as well the piston pins. Piston pins are basically thick-walled hollow tubes like the rest of the piston and connecting rod assembly. It's built to be strong and light. Most are made from alloy steel and are plated with chrome and carbonized and heat treated to provide good wear resistance. Piston pins are lubricated by oil fed through passages in the connecting rods, oil splashing in the crankcase or spray nozzles in the rods or pistons. Also, a piston pin fits through the small end of the connecting rod and the piston's pin bore, and the way the pin is retained is used to describe it. The first one, a stationary pin, is pressed into the piston and the connecting rod swivels on the pin, or a semi-floating pin is pressed into the connecting rod and the piston swivels on the pin, and a full floating pin is able to move or rotate in the piston and connecting rod. The pins are retained by caps, plugs, snap rings, or spring clips inserted in the piston at the ends of the pin. Full floating pins are the most commonly used. And we will move right now to the piston rings. Piston rings are used to fill the gap between the piston and cylinder wall. The piston rings seal the combustion chamber at the piston, and piston rings must also remove oil from the cylinder walls to prevent oil from entering into the combustion chamber. They also carry heat from the piston to the cylinder walls to help cool the piston. Also, in most engines, pistons are fitted with 2 compression rings and 1 oil control ring. The compression rings are found in the 2 upper grooves closest to the piston head, and the oil ring is fitted to the groove just above the rest pin. So there are many different designs of rings, each have specific applications. And we will go more in depth to describe the compression rings. Compression rings are designed to use combustion pressure to force them against the cylinder wall. During the power stroke, the pressure caused by the expanding air-fuel mixture is applied between the inside of the ring and the piston ring groove. This forces the ring into full contact with the cylinder walls. The same force is applied to the top of the ring, forcing it against the bottom of the ring groove. These 2 actions help to form tight ring seal. Also, we have oil control rings. Oil is constantly being applied to the cylinder walls. The oil lubricates and cleans the cylinder wall and helps cool the piston. Controlling this oil is the primary purpose of the oil ring. The 2 common types of oil rings are the segmented oil ring and the cast iron oil ring. Both are slotted to the excess oil from the cylinder wall can pass through the ring, and the piston's oil ring groove is also slotted. Oil presses through the ring and slots in the piston and returns to the oil sump. Segmented oil rings have an upper and lower scrapers, rails, and an expander. The scraper rings are often chrome rings. The expander pushes the 2 scrapers out against the cylinder wall, and during installation, the end gaps of the 3 pieces must be staggered to prevent oil from escaping into the cylinder.